In this module, we shall discuss some interesting examples of subgroups. As you have seen in the previous modules, that the set of all square matrices of order n by n having determinant not equal to 0 form a group under matrix multiplication. If F is a field, GLNF denotes the group of all invertible n by n matrices over F under the multiplication. This group is called the general linear group of degree n over F. And here we shall find the subgroups of GLNF. An interesting subgroup of GLNF is T plus NF, the set of all n by n upper triangular matrices over F. That is n by n matrices of the form A11, A12, A13, A1n, 0, A22, A23 and so on, A2n, 0, 0, 0 and so on, ANN. This is the upper triangular matrix, and in linear algebra you have studied that when we multiply two upper triangular matrices we shall get an upper triangular matrix, and when we find the inverse of upper triangular matrix we shall get the upper triangular matrix. So in this way we can prove that it is a subgroup of GLNF. You shall study later the theorem in which we shall prove that we need to check just two axioms for being the subgroup of a group G. The first axiom is that closed under multiplication, the binary operation star say, and the second axiom is existence of inverse. Here each diagonal entry is non-zero because the matrix is Here each diagonal entry is non-zero because the matrix is invertible. If there is a 0 in diagonal, then we shall get determinant equal to 0. Similarly, the lower triangular matrices, which is denoted by T minus NF, form a subgroup of GLNF under matrix multiplication. And the lower triangular matrices are denoted by this. You can see that here the entries Aij's can be non-zero or 0. So this is lower triangular matrix, but the entries above the main diagonals must be 0. Such matrix is called lower triangular matrix, and when we multiply two lower triangular matrices we shall get lower triangular matrix, and inverse of lower triangular matrix is lower triangular matrix. In this manner we can say that T minus NF is subgroup of GLNF. Now we see some more subgroups of GLNF. Diagonal matrices D and F, it's closed under multiplication, identity and inverses simply because each of T plus NF and T minus NF are. This is a special case of general fact that intersection of any collection of subgroup is itself a subgroup, and you can see that diagonal D and F, set of all diagonal matrices, is the intersection of upper triangular matrices and lower triangular matrices, and upper triangular matrices form a subgroup of GLNF you have seen earlier, and also lower triangular matrices is subgroup of GLNF. So their intersection is also a subgroup, which is a set of all diagonal matrices of order n by n with entries in F. And here is the representation of diagonal matrix. You can see that the entries in the main diagonals are non-zero and remaining entries are 0. because क्योंकि ये invertible matrix है तो हर entry diagonal में non-zero होगी, otherwise ये invertible नहीं रहेगी. Within D and F we find a subgroup S and F. These are simply the diagonal matrices that have the same non-zero entry down the diagonal. That is non-zero scalar multiples of the identity matrix. You can see here in the diagonal lambdas are appearing and remaining entries are 0, and we can take lambda out, and this is an identity matrix lambda in, and this is the matrix of S and F in general form. Now we are considering some more subgroups of GL and F. Uni upper triangular matrices. There are the upper triangular matrices with ones down the diagonal, and its representation is in this form. In the main diagonal, ones are appearing, and above the diagonal you have arbitrary real numbers, numbers from the field F, A12, A13 up to so on A1n, A23 up to so on A2n, and this forms a subgroup of GL and F, and you can verify it using linear algebra. Uniloyer triangular matrices, these also form a group under multiplication. This is a subgroup of GL and F, and the representation of the matrix is in this form. Here in the main diagonal ones are appearing, and below the main diagonal there are non-zero entries, and it can be 0. Aij's can be 0 or non-zero, but the entries above the diagonal must be 0. Now we have constructed a subgroup diagram. G, L and F is a group, and its subgroup is upper triangular matrices of order n by n with entries in field F, and T minus NF is lower triangular matrices of order n by n with entries in field, and it is subgroup of GL and F. And the diagonal matrices are subgroups of upper triangular matrix and lower triangular matrix. Uni upper triangular matrix is subgroup of upper triangular matrix. Uni lower triangular matrix is subgroup of lower triangular matrix, and SNF is subgroup of DNF, and the identity matrix is subgroup of uni upper triangular matrix and uni lower triangular matrix. And you can see that the matrices of order n by n with entries in field, and you have seen that set of real number form a field, set of complex numbers, set of rational numbers form a field, and in case of field it would be a group under matrix multiplication. If here you replace F by Z, Z is not a field, then you shall get not a group under matrix multiplication in general. Another very important subgroup of GL and F is SL and F, consisting of all the matrices with determinant 1. It's called the special linear group of degree n over F, and it would be a good assignment for you that you should show that SL and F is subgroup of general linear group of order n by n with entries in F, and you just have to prove just two axioms, closed under multiplication and existence of inverse. So you can try it at your home.